Good morning, afternoon, or evening. How y'all doing today? Welcome back to Morrow's Math Corner. Today we're going to learn how to graph quadratic functions using transformations. So let's get right to it. Let's remember that the parent quadratic function will always look like so. Y equals ax squared. I went ahead and graphed here in red the most basic of quadratic functions, just the regular old y equals x squared, where a is 1. When I go ahead and plug in my Morrow 5 into the x values, I get this beautiful quadratic function graph, this beautiful parabola. That is the most basic quadratic function that we can have. And we're going to use this a lot today to investigate transformations. Now, the vertex form of quadratic functions, or of any function for that matter, is a manipulation of the parent function. A quadratic parent function, once again, looks as so. Y equals ax squared. But this parent function can be applied to absolute value functions, square root functions, cube root functions, rational functions, etc., etc. This works for any kind of function. We're just going to go ahead and investigate how it works with quadratics for today. Now, the vertex form of any function is y equals a times x minus h squared plus k. It's squared in this case because it's a quadratic function. But once again, that h and that k can be used in an absolute value, a cube root, a square root function, any function of any sorts. For example, I could write a vertex form for a square root function as so. A times x minus h plus k. So the h and the k properties that we're going to learn today can be applied to any function. So let's get to it. First and foremost, the a is very important when analyzing a quadratic function or any function for that matter. If a is greater than 0, in other words, if a is positive, then we're going to have a parabola that points upwards, as you can see here. If a is less than 0, in other words, if a is a negative value, then we're going to have a parabola or function that points downwards, as so. Now, beyond whether it points up or down, regardless of if it's positive or negative, if the absolute value of a is greater than 1, then the graph stretches vertically and becomes narrower, which is a vertical stretch or a horizontal compression. So I went ahead and I already graphed the parent function y equals x squared. Let's go ahead and graph y equals 2x squared so you could see what happens as a gets larger and larger. I'm going to once again use my Morrow 5 here. And it's going to give me the values of y equals 8, 2, 0, 2, and 8 once again. So I've got 0, 0 here. Now I've got negative 1, 2, 1, 2, and then I've got 2, 8, and 2, negative 8. And as you can clearly tell, that is much more narrow. So if the absolute value of a is greater than 1, the larger the a is, the more narrow it becomes. So that is a vertical stretch or a horizontal compression. Now, if the absolute value of a is greater than or equal to 0 or less than or equal to 1, and actually that's a mistake here. It should just be greater than 0 and less than 1. I apologize for that. If the absolute value of a is greater than 0 or less than 1, then the graph compresses vertically. That means it shrinks down and becomes wider. And this is known as a vertical compression or a horizontal stretch because it's compressing vertically, but it's stretching horizontally. Let's go ahead and once again we have the parent function in red. Let's go ahead and graph y equals 1/2 x squared in blue so you can see what happens in a vertical compression. Remember that whenever you have an a that's a fraction, use multiples of the denominator. So that way you don't have any fractions. I'm going to use -4, -2, 0, 2, and 4. So we've got -16 over 2 is 8. 2 over 2 is 1, 0, 0, 2, 1, and 4, 8. So let's go ahead and graph that. So I've got my 0, 0. I've got my -4, 1, 2, 3, 4, 8. And then I've got my positive 1, 2, 3, 4, 8. Then I've got -2, 1, and +2, 1. And as you can see, it's clearly wider than the parent. So once again, if the absolute value of a is greater than 1, I have a vertical stretch and it becomes narrower. If the absolute value of a is greater than 0 but less than 1, in other words, it's a fraction or a decimal, then it's going to become wider. That is a vertical compression or horizontal stretch. Okay, let's investigate the h. If you have x plus h, the h is actually negative. So the graph shifts to the left that many spaces. The h in reality is always opposite of what's given. So literally, if I have my parent here in red, if I have x plus 3 squared to shift or to graph, I'm going to literally shift it 1, 2, 3 to the left. Then this point here, 1, 2, 3 to the left. Then 1, 2, 3 to the left. Then 1, 2, 3 to the left. Then 1, 2, 3 to the left, literally, and that would be my new function. So I'm going to go ahead and use a pointer here. So my first point here, I went 1, 2, 3 to the left. Then 1, 2, 3 to the left. Then 1, 2, 3 to the left. 1, 2, 3 to the left. 1, 2, 3 to the left. Okay. If you have x minus h in the parentheses, the h is actually positive and the graph shifts to the right that many spaces. Because remember, the actual h is always opposite to what's given. So I already have my parent here in red. I want to graph x minus 3 squared. Well, literally, now I'm going to go 1, 2, 3 to the right, and then 1, 2, 3 to the right, then 1, 2, 3 to the right, 1, 2, 3 to the right, 1, 2, 3 to the right. So let's go ahead and do it. So I got 1, 2, 3 to the right for my first point, then 1, 2, 3 to the right, then 1, 2, 3 to the right, then 1, 2, 3 to the right, then 1, 2, 3 to the right. And you literally have just graphed your new function with the horizontal shift. So once again, I went 1, 2, 3 to the right, 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 1, 2, 3 to the right. So that's how h works. Okay, let's investigate k. If the k is positive, the graph shifts up that many spaces. It's that simple. So literally, if I have here, I want to graph y equals x squared plus 2. From my parent that I already have graphed here, I'm going to literally shift each point up 2. So this first point, I go up 1, 2. This next point here to the left, up 1, 2. Next point here to the right, up 1, 2. So other point here, 1, 2. And this guy over here, 1, 2. And I shifted my graph upwards 2. So with our pointer, we literally took this point and went up 1, 2. This point 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 went up 1, 2. And that's a vertical shift, a k of 2. If k is negative, the graph shifts down that many spaces. So in this particular case, I have x squared minus 2. So every single point will shift down 2. So I'm going to go down 1, 2, down 1, 2, down 1, 2, down 1, 2, down 1, 2. And that will be the graph of my new function, shifted down 2. Using our pointer, I literally took this point and went down 1, 2. This point here 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 went down 1, 2. And that's my k. All right. So now, if I wanted to graph y equals x squared plus 2 squared plus 1, I can absolutely graph my parent and then shift 2 to the left every single point and then up 1. But that's a little bit cumbersome, so let me show you a much better and more efficient way to do so. First and foremost, find and graph the vertex. The vertex is hk. Remember that the h is always opposite of what's given. So I have x plus 2 squared plus 1. So my hk is negative 2, 1. Next, find and graph my y-intercept. Go ahead and plug 0 in for x and find your y-intercept. 0 plus 2 is 2. 2 squared is 4 plus 1 is 5. 0, 5 is my y-intercept. And then, please pay special attention to this. If the vertex and the y-intercept are the same ordered pair, plug in any value for x and find the corresponding y value. Then graph the ordered pair you found along with what's called its mirror image. Or you can go ahead and solve for the x-intercept by factoring, completing the square, the quadratic formula, or the square root method, and that will give you the x values on the x-axis, and you can use that as an extra set of points as well. So let's look at what I just told you to do here. I've got here, my vertex is negative 2, 1. So I've got negative 2, 1, negative 2, 1. My y-intercept, we said, was 0, 5. So 0, 1, 2, 3, 4, 5. Okay. Now, down the vertex, there's an invisible line, this dashed line here that I'm writing. That is called the axis of symmetry. The axis of symmetry cuts a parabola into perfect halves. Kind of like when you were a kid and you would draw a little heart on a folded piece of paper, and then when you would cut out just that half of the heart, you would unfold it and you would have a perfect heart. Every point would match up. That's symmetry. So I have my y-intercept here of 0, 5, and if you notice, that is 1, 2 units to the right of the axis of symmetry. We'll find the mirror image by literally going 1, 2 units to the left. So I've got another point here, and ta-da! You've just graphed a quadratic function. Now, what about step 3? What if I wanted this a little bit more detailed? Go ahead and just make an XY table. Let's go ahead and find the value of y when x is 1. Well, 1 plus 2 is 3, 3 squared is 9, plus 1 is 10. So let me go ahead and erase this here for you. So I've got 110. So I've got here 5, 6, 7, 8, 9, 10. And then the mirror image of that. So that's 1, 2, 3 to the right of the axis of symmetry. So you're going to go ahead and put another ordered pair at 1, 2, 3 to the left of the axis of symmetry. And that's what I mean by make a table, find one value, and then plot the mirror image of that particular value. And in this case, it does not cross the x-axis, so solving it would be a moot point because there are no x-intercepts. And there you have it. That's how you graph like a boss. Okay, now, what if it's not in vertex form? What if the function that they're giving you is not in vertex form? What if it's in standard form? Well, we're going to want to write the standard form of y equals x squared plus bx plus c in vertex form, y equals a times x minus h squared plus k. First thing we're going to do is we're going to go ahead and separate the c. So I'm going to go ahead and put parentheses around the x squared and the 8x, and I'm going to literally separate the c, which in this case is -5. And now I'm going to complete the square. And when I complete the square, I'm going to subtract the b over 2 squared from the c instead of sending it to the other side of the equation. Because we're not solving here, we're rewriting. So we're going to use the completing the square skill, but to rewrite it. So our b here is 8. b over 2 is 4. So we've got 4 squared, which I'm going to subtract from the c. Now we're going to go ahead and factor the perfect square trinomial. Simplify and write in vertex form. Y equals a times x minus h squared plus k. Well, we know that the square root of x squared is x. We know that the square root of 4x squared is 4. And we're going to square it because that's how we complete the square. And then -5 minus 16 is -21. And there you have it. You just completed the square. You took a standard form and you went ahead and used the completing the square method to rewrite it into vertex form. Now from here, I know that my vertex is -4, -21, and my y-intercept when x is 0 is 4 squared, which is 16 minus 21, so that's 0, -5. Now I can graph both of those, graph the mirror image, and voila, we're done. Okay, next. What if we have it in the form of ax squared plus bx plus c? For example, I want to write y equals -3x squared plus 6x minus 1 in vertex form. Well, first things first, just like before, I want to go ahead and separate the c from my y equals ax squared plus bx plus c. Then I want to factor out a from the ax squared plus bx and subtract it from c. So what did I just do here? Okay, let's check it out. I'm going to go ahead and isolate the -3x squared plus 6x. So that's how and why I have my -1 outside here. But I want to go ahead and make sure that I factor out whatever a I have from this term in here, from these two terms from this binomial. So I'm going to divide -3 out. So that's where this -3 comes from. -3x squared divided by -3 is x squared. 6x divided by -3 is -2. And that -3 that I just factored out, I subtract it from the -1, the c that I isolated. Now, once again, I'm going to complete the square, and this time I'm going to multiply it to the factored out a. So, when I complete the square here, my b is -2. -2 divided by 2 is -1 squared. That's my b over 2 squared value. And I'm going to multiply that b over 2 squared value to the a that I factored out. So now, how do I write this in vertex form? Well, I have my a, which is -3, times the perfect square, which I just created. The square root of x squared is x. The square root of -1 squared is -1, and I'm squaring it because I completed the square. And then if I calculate -1 minus a -3 times a -1 squared, I'm going to have -1 squared is 1, times a -3 is -3, times a -1 is +3, minus 1 is +2. And we are bingo. And now, once again, my vertex is 1, 2. My y-intercept, when x is 0, I've got -1 squared, which is 1, times -3, which is -3, plus 2, so that'd be 0, -1. I can graph both of those and be on my way. And there you have it. Hope you learned a lot. Thank you for watching. Come back anytime. Take care now. Bye-bye.